There we go.
You can hear it too.
All right, today we're going to look at our second structural material, and by that we're going to deal with carbon steel, or steel as you call it. Now when we talk about this type of material, which I have a bunch of it up here, it evolved for quite a bit. In fact, it's still evolving as we move through and get more technology. This has been around, I think they found stuff, according to the documentation I've seen, around 6,000 years ago, so it even predates like the Roman civilization. Now certainly the stuff they had back in those days was, they're digging up iron, they never really had smelters at that point, so they were just kind of using it and hammer it into shape. But once we got fire, we were able to start melting it, and we started adding stuff to iron, and we call it carbon. Okay? So carbon is the material that then we add to iron to make it much more rigid. So steel, it is basically iron and carbon in varying amounts. Because iron itself is a metal a lot like gold or silver or something of that nature. You can take it, you can hammer it into shapes, and you can do things with it. It's really not that strong by itself. We have to add stuff to it to make it strong. Okay? Hence the carbon. Now certainly we add a lot more than carbon to it in today's world. We call those alloys. So the big thing I want you to know about steel, it is our all-purpose material. It excels in tensile forces. Excels. In fact, there's not much that's better. It has the same strength characteristics in compression. Okay, so it does great in compression. It does great with shear, it does great with torque. It's just a good all-around material. It is our strongest material that we use for building per volume. It's not our strongest material, but per volume. So what does that really mean? You're going to actually hear me say tomorrow, wood's stronger than steel per weight, and it is. And we have a lot of materials, like they found spider webs that are stronger than steel. But of course we can't get a lot of spider webs to make a building. Yeah, I was watching a documentary, just kind of an aside, a little rabbit trail, about some spider they found down in the Amazon, and its web is 6 times the strength of steel. But of course you can only get one strand, and kind of hard to build something like that. All right, but this stuff right here, what I mean by it is the strongest material per volume is we can put a lot of this material in a small area. It weighs a lot, so it creates a lot of forces on its own, very heavy. So it's something, if we go very, very high with stuff, we generally try and keep steel out of the top reaches because it just weighs so much, and we got to support it down below. Okay? Now certainly we'll run stuff all the way to the top and supporting structures using this, but then we'll switch to other materials inside. Okay? So that's steel. It's really our all-purpose material. This stuff right here, when we use it for structural, you're going to use 2 types in structural. That means different amounts of carbon are added. By the way, the less carbon you add, the more ductile or flexible the steel is. If you add a whole bunch, it gets very brittle, but it gets strong. Okay, so if you add just a little bit of carbon to iron, we call it 36K steel. And what that means is its tensile strength is 36,000 pounds per square inch. Which means if you had a square inch of it, you could hook 36,000 pounds on it, pull it up, and it would not fail.
36,000 pounds per square inch?
Per square inch. That's what it will withstand. Okay, that's what we call mild structural steel. Okay. We also have a very high ductile steel that we also use for structural. We add more carbon to it, and it is 60,000 PSI material. Okay. So it will stand 60,000 pounds per square inch.
Does the carbon make it heavier?
No, no, the iron's the heavy component.
So the more carbon you add, it doesn't get lighter, does it? Or is it
Yeah,
about the same?
it's going to get lighter. It's not a huge amount. So, I mean, you cannot pick up a 36K and a 60K piece of steel and tell by weight. You can't tell it. Now, if you put it on a scale, yeah, you can do it because it's just a molecular equation, right? We got a chemist in the room, she could probably do that in her sleep, where she could tell you exactly how much.
Once upon a time.
Yeah, math with letters, gotta love that stuff. Yeah. All right, so, and that's kind of the general rule of steel. So it's our all-purpose, strongest per volume. Let's look at how we use it in structural steel. So again, we're going to be bouncing around chapter 42 a little bit and look at. So we use this everywhere. We use it for foundations, we use it for floors, we use it for walls, we use it for roofs, we use it everywhere. Now let's look at walls. First one I'm going to look at is actually back in chapter 28. So figure 28, 27. Pages 702, if that helps you. Now I have a couple metal studs in the back, and I didn't pull them out because I pulled them out in architectural, but if anybody wishes to look at these in a little more detail, like I've got two different types that I've saved over time. So here we see it being used for walls. Okay. Now this is really a thin carbon steel. Usually it's 36 KSI. Here you can kind of see it being put together as a bottom plate, and then you see the studs coming up. You use the exact same characteristics as wood, so we still do it 16 inches on center. It's got holes for your electrical and plumbing and all that to go through it. Now the reason this is kind of used commercial and not residential is that generally you need some extra tools for it, and they just cost a little bit more, okay? Much more than a hammer and a skill saw. Okay? So in essence, it is used real, in fact, every wall in here that is not a concrete wall is a steel wall. That one is, this middle one is, okay, those are all steel walls. You can't tell the difference, we still put drywall on them, all of that. What's the advantages of going with a steel wall over a wood wall? Well, a couple. Okay. Certainly not the cost. It's a little more expensive than wood. It's a little harder to install, you need a special workforce. But it is dimensionally perfect. Okay. The stuff doesn't change over time. In fact, you can take that, a galvanized piece, throw it out in the mud for 3 years, pick it back up and still use it. Okay. So it's that, and then also, if you've ever worked with wood and you're trying to put drywall on it and you got 2x4 that's warped like this, hey, you got to cut the thing out and put a new one in. This will never happen to this stuff. When it calls out and says this is 3.5 inches, it's 3.5 inches the entire way. So that's really the big advantage, is that it's dimensionally perfect and it holds its shape over time. So there it is being used as walls. Let's turn to page 704. And we got another picture kind of depicting the same thing, but they do add joists. Now here you see the studs, and then on running across the top of them here you see joists. Again, this is very thin metal. You know, it's got this shiny look on it because it's typically galvanized, which is an electric plating device. In essence, they charge a vat of this material, drop it in there, and then the electrons attach it, and kind of like painting, right? But it protects it from the elements. When you look at these and you look even the studs, they're all going to be a channel shape. And I've got one piece of channel right here, which is kind of this C-looking shape. Okay. Now, this one here is a real structural piece of channel. This stuff doesn't have the big wide portions down at the bottom. Okay. So it's pretty much straight. Okay. So here you see it being used as walls and floors. So it's carrying the platform. Please stop me if you have any questions.
So when they're building the house, though, didn't we see it where they had that and then you put the wood in it?
Yeah, inside of it. Yeah, like for door frames and stuff. When we
Yeah.
need a fastening device to hold it. It's one thing is the steel that is used for walls and joists and stuff, since it's so thin, it is susceptible to buckling. By that, you put enough weight on it, it won't resist the force. That's why one of your questions for review is how high can you go with this stuff? And I think they recommended don't go above 5 floors. Because once you get, the higher it gets, the more it's gonna be susceptible to buckling. And that's what this stuff is kind of like. You want to be a little careful with it. And you, especially whenever you screw into it, you kind of get that. You can't really see it in either one of these pictures. But I'm going to go back one picture and kind of readdress that question. And maybe I should have pulled those out and I could have showed you. But you'll notice that this one's a little bigger piece, but it's kind of the same concept. See how there's that little tray in there? Well, since this thing's 3.5 inches, you can take a 2x4 and actually slide it right into that area. Okay? And then these flanges that are sitting on the edge are the same width. Okay? And it just snaps right in. And then from there, that gives you something where you can screw into it without deforming those and weakening them. That's where we use them. Okay? Only around window frames, door frames, when we need a fastening device.
Okay.
Okay? But other than that, it's just fine. I've always heard, don't do a steel building because you'll never hear the radio. Or it'll screw with your cell phone. I've yet to see that. Personal observation is I've been in a few homes. My dad had one. I helped him put it together, and yeah, we got cable. Everything worked just fine. Cell phones worked. Everything was good. Any other questions on that? Okay. All right, let's go look at some more. That's really walls and joists, which are structural items, of course, but not like what we really attribute structural steel for in the commercial industry. Now we're going to look at some of that. So back to 42, figure 4225. Okay, we looked at this picture yesterday, but we looked at it for the steel decking, which of course is again another platform steel device. But here, I wanted you to see the beam setup. And I kind of wonder as I do this why I'm using pictures when we got all this stuff sitting in the hallway too. And certainly I think we need to walk out and look at some of the jointing, which we'll plan on hitting on Monday for that. But that won't stop you and lectures out to get out and go walk around. That's one of the reasons this building was left open, is so that you folks can see that stuff. Yes, Sherry.
So when we talked yesterday about the steel decking, one thing I wasn't sure about was you leave that in place, don't you?
Mm-hmm. Yeah.
Okay, so you don't have to worry about the weight of the steel or the weight of the deck.
No.
Okay.
But I mean, yeah, we would calculate it once we knew it, but remember we used 20 pounds of dead load just as an all-encompassing value.
So that rolls into the dead load.
Yeah, and that would roll into the dead load. So here we see the beams up. That's kind of what we're looking at this picture for. So here we have a main one. Here we have one that's acting a little bit like a purloin. So where these might be considered like girders. Remember we talked about girders in a roof. They're a main supporting beam. And then we have purloins, which then do intermediate spans. Okay. And here you see that setup. So this one's supporting the steel deck up above it. Good look at them. It's hard to see in this picture, but if you look in close on those joints, you'll see these joints done several ways. Generally, they are bolted when you put them up. Okay? So they might have a bolt hole or two. Now the bolts could be the connection device themselves. Sometimes we'll just put a bolt in to hold it long enough for a welder to get up there and permanently fasten it with a weld. Sometimes we do both. That joint that's in between those two. And we'll talk, like I said, we'll talk about jointing on Monday. Okay. We got some more beams. Let's go to figure 35, page 1070.
And is it the same thing where it's, sometimes it's K 36 and sometimes it's K 60, or is it, are these always?
They're typically 36 in a building. You can get 60,000 PSI stuff, but we only use that in extreme situations. So here you see kind of all scenarios. So we have some big beams coming through. We also see it in a column. Okay. That's the supporting structure of the structure. You see the walls in here where they've got really those floor joist channel pieces that are filling these spaces in as walls. These aren't carrying anything. They're just filling the space in. What you're carrying the loads with is this beam and columns. I just got a little backwards as I pointed to them. I always get those two mixed up. And of course, the same one we looked at for girders and purloins. Here you see some kind of custom columns and beams in place. And it was kind of nice, those of you that got the chance to go to Boise and Western Trailer. Remember seeing these things being made where they were using plate steel through here? Then they had an automatic welder that then welded plate steel to the top for their truck beds. Same process for these things. These are generally, I'm sure they can forge them, but generally they're made in some plant out of plate. I couldn't really find, the best picture I could find of a truss system is figure 4237 in our text. And this is a box truss. And here you can kind of see we're using, in this case, it looks like angle to create a supporting structure. A box truss is what we'd call this. But pipe works really well for this stuff too. And in fact, Sean, where you do all your practicing in the Expo Center, if you ever get a chance to climb into that roof, it is a truss system that is nothing but, I think it's 3/4 galvanized pipe. And there's quite a few of them up there. But that's how they span that huge distance, is with those trusses. You can use it for that also. Now, keep in mind, we're seeing it as a structural. You use steel in a lot of different ways. We have straps all the time. Okay? And go back to your foundation chapters. You're going to see straps everywhere where we're tying concrete to wood or something of that nature. Nails are a steel function, right? I usually talk about nails, and we will be talking about nails. We're going to come into it when we talk about wood. Okay? Because in essence, it's a steel product. It's carbon steel. But at the same time, we're only using it for this material. Okay? So it kind of goes more with wood. Hangers. Okay? Look back into the floor chapters. You're going to see hangers everywhere on those engineered floor joists, on beams, the whole 9 yards. They're always done pretty much with metal. You have a lot of little miscellaneous additives. Maybe a big one I never mentioned, rebar. We talked about it yesterday, right? Good marriage there with concrete and steel. So we have a lot of different places we use it. As far as the plans go, any questions so far? The plans for this stuff is awesome. It's a line drawing. Okay? This is figure 4241. You're going to see two types of drawings used with steel. You're going to see a plan type view, which is like this one. Okay? So here we just see a bunch of lines, and we have some text laid along the lines. And we're just calling out the material. Okay? So in essence, if I look at this line right here, I use some line type, they've got it as a center line, and they just label right along it W12 by 27. That tells you what you're getting. So you're going to put one of these guys up there. Now on top of that, we've got some other things going on. We've got these pieces coming along. The C means a channel, okay? So it's a channel 10 by 25. That's also going to go up there. Okay? In essence, pretty tough drafting, isn't it? Draw a few lines, put a little text on it, and you're walking away from it.
Now, does the W mean?
We're going to come into that in a second. W means wide flange beam. So there's the drafting for it in the plan view. Now, this may happen, this type of drawing is what you find in an engineering architectural office. Okay, this is what an architectural or a civil or a mechanical drafter would put together. At some point, we go to the detail stage. This may happen in an engineering architectural office. It may happen at a fabricator. Okay? Not all the time people have the skills to do steel detailing in an engineering office. That's really not what they're there for. Okay? They're there just to say, this thing's going to carry it, somebody else figure out the jointing on it. And so it would go to somebody like K&T Steel, where they have fabricators and detailers, and that's what they do. In fact, a student from last year's program's over the lead drafter at K&T right now. They've got another one at Charmat, which is doing the same thing. And so those jobs are out there doing that type of stuff. When you talk about a detail, you're going to the opposite page where we start looking at like figure 43B. Okay? Where here you see a detail drawing that is showing that wide flange beam, but here we're going to say, oh, I need a hole cut here for a bolt to go through. So you're going to dimension that hole and locate it. Here we're going to put some clips on it for something, so we're going to add some material to it, cut some holes in it or whatever the case might be. Here they're coming in, call this a coat. They're going to coat the top of this because it's going to be welded or bolted right here onto another one. Okay, so here's where they would do the multi-view drawing of the beam for fabrication. Okay? That's called detailing. And in fact, these drafters are the only ones out there that can call them detailers, because that's what they do. Okay? Multi-view drawings of steel. And you got quite a few of these around here. Another real good one is figure 4246, for detail. So here we have a 2-view drawing that's showing how we have some type of beam coming along. Okay, we're going to put a plate on here, we're going to cut some holes in it to bolt. Here we're going to have this column come up, we're going to weld something on right here, it looks like a little stiffener, to put it in. So this is my top view, that's my front view. Tells everybody what I need to do to put that together. Nothing new there. Okay. All right, that's kind of it on steel, other than the standard manufactured shapes that we can buy from a foundry. Okay, so any questions before we leave drawings and stuff? Okay. And again, that drawing set back there has a lot of details on this. It'd be a good resource for you to browse through. All right, so let's look at the shapes. Now, we have some that are pretty similar. Notice like right through here, we have these 4 that look through here. Do you see any I-beams in there? Because that's what everybody calls these things, right? That's a generic term. Walk off the street, oh, that's an I-beam. We actually don't make I-beams. There's really no such thing in today's world. In essence, the closest we can get to an I-beam is this pile, the HP shape. Okay, that's like the old I-beam. What we've now done is we've changed these shapes, since we're getting these things that are actually cast, that we can go ahead and do them for different situations. So when we do these, we've got to call them out by the right ones. The most common is a W shape. It's a good generic one, it has a wide enough flange at the top. By the way, when you're looking at these shapes, the top piece is a flange. That's the top and bottom. The middle piece is a web. W shape is the most commonly used one. It's a good all-purpose one. We can use it for columns, we can use it for beams, we can use it for everything. The S beam is the next one. Now the S-beam, notice the difference in the shape on these two. Okay. And I actually have the two, and I'm going to pass them around so you can look at them right now. Okay. So these are very similar to what they can do. This is a W shape. Now pay attention on this one to this area right up in here, because we put a weight on this, right? And due to the web, this side is carrying this side, but now I've got a moment arm, so it carries more, right? That's what the web's for, is to connect those two so we can get that lever action going. Makes it a lot stronger. But when you see this top piece right up in here, what that's for is so you get a weight and then something deflects on this side, something deflects on that side. How is it going to work with the web in the bottom piece? Will it kind of roll and fluctuate, or won't it? Look at the one on this one. It is much, much thicker. Okay? So this one doesn't this one's, I'm saying this backwards. This one does not handle sideways loads as well as this one. Okay? But I can get more weight on this one for how much material I use. Okay? So this is an S shape. This one's a W shape. And just kind of look at the differences.
This doesn't look anything like an S.
Doesn't look like what?
An S.
That's a W.
Oh, well, this doesn't look like an S either.
No.
I guess maybe it's the
Yeah,
back.
it's the big filament surface in there. So those are our two biggies right there. Okay. I have seen M shapes used quite a bit. The M shape is a little different in that the flanges get wider, okay, on the M shape. So the flanges are wider. They're a real heavy beam, the M shape. And then of course you got your pilings, which are our old I-beams. They look basically like an I-beam. When we say pilings, these are the types that we usually protect somehow. We're driving them down in the mud